Okay, so today I'm going to give you one lecture about signature schemes. So signature is normally when we sign a document. So physically what we do, right? We take a paper and we sign it, right? Or if you want to take money from bank, you sign a check, right? And then the person there can verify that signature. Or sometime earlier, even in the credit card, at the back side you need to sign and then they need to verify when you are doing the payment. But now you can use PIN and so on, right? So basically, the idea is the same concept of signature. How do we do it in the online business, right? How do we do the digital signature? So there are a couple of challenges, right? For example, if you sign a document using some digital signature, so it's kind of you bind to your message your signature, right? So everybody should be able to sign its own signature. So there should be some sort of privacy to it, right? Somebody is signing, and there should be some sort of verification algorithm, which is known publicly. So anybody who wants to verify whether this is signed by you, they can verify. So these ideas basically give rise to the thinking that maybe we can use RSA crypto system for these kind of things, and actually we can use RSA crypto system for digital signatures. We can also use Elgamal crypto systems for digital signatures. So I'm going to describe these two, and there are many others, but I'm not going to touch it. And so once we are doing this, obviously the most important part is the security of these systems, right? So I'll describe in general some strategies, what are the attacks possible on such things, okay, and how to do a forgery, right? So another very important problem is that if you sign a document digitally, and so suppose you want to send some money to third person and you sign it once and digitally, right? So how, if whether the person is going to use it again, so how do you stop that? So all kind of issues are there when we actually take this idea of signature into the digital world, right? So what are the digital signature schemes? So there are essentially two parts. I'm going to start and then I'll give you the brief idea about these two algorithms. So signature schemes. So there are two algorithms which are used in signature schemes. One of them is signing algorithm. Another one is verification algorithm. Okay. So these are the two important one. So if there is a message X, okay. So we sign algorithm will work for some private key. Okay. K is our private key. So you can sign the message. This is private, right? And this verification algorithm, you use some function verification or verification algorithm. This is public. Okay. So this signing algorithm, because each individual can sign the record, right, or the digital message. So they will have their private key, right, to sign the thing, right? So suppose I am signing a document, I can use my own key to sign the document, and anyone else in the crowd can verify it using some public algorithm, whether it is signed by me or not. Okay. So essentially we are having a pair x comma y, where x is nothing but a message and y is a signature on x. Okay. So what verification algorithm will do? Verification algorithm will work on the pair x comma y, and the output is either true or false. True if y is nothing but signature of x using k, and false if y is not signature of Okay. So essentially, we transmit this pair x comma y. So x is a message and y is a signature on x. Okay. In fact, you will see that some similarity with hash function. In fact, we are going to use hash function. I'll show you that idea. And so basically, you sign x using your private key, and then there should be verification algorithm which is available publicly, and verification algorithm will check whether y is signature of x with key k. If it is, then it is true, otherwise it is false. Okay, so this is a very simple methodology how it is going to work, right? So more formally or mathematically I can describe this. So this is the general idea about signature scheme. How do we describe this mathematically? So I am going to do that now. Mathematically, it is nothing but a 5 tuple P, A, A, S, and V. 5 tuple. What is P? Finite set of possible messages. A, finite set of possible signatures. And K, our key space. Again, finite set of possible keys. Now, for every small k into capital K, for every key, there is a signing algorithm. Call it as sign of K belongs to S. Okay. And a corresponding verification algorithm. Belong to this set. Right. So I can say that signing algorithm from P to A. Okay. And so these are some sort of functions, and verification algorithm from P cross A to true or false set. And for every X in P and for every signature Y in A, this is signature. Verification of X comma Y is true if Y is signature, Y is sign of KX, and false otherwise. Right? So finally, a pair X comma Y with X in P message and Y in A signature, okay, is called a signed message. So essentially whatever I told you, the methodology, one can write it mathematically. So P is a set of finite set of possible messages. A is finite set of signatures. K is a key space, a finite set of possible keys. And for every small k into capital K, so this is a key. For each key, there is a signing algorithm. Sign of K, essentially it's a function from P to A. Okay. Uh, and a verification algorithm, corresponding verification algorithm, verification VRK, which is again a function. So VRK is acting on this pair and telling you whether it is true or false, right? So for every X in P, or whatever you call it as a plain text or message, for every message and for every signature, we can do this verification function, right? Verification algorithm can run and tells if y is signature of x, it is true, otherwise it is false, right? So essentially, this pair x comma y is known as signed message. Okay, just capturing mathematically. So I hope you understood what is a digital signature scheme, right? Something not very difficult. Now I think based on, so now you can one you might guess that we can use some sort of function from RSA crypto system. You know, maybe RSA crypto system should be used because there is also public key and private key, those kind of things, right? So the private key of the RSA crypto system can be used to sign the signature, and there should be another function which we should be used to verify. Okay, so let us describe that RSA. So signature scheme based on RSA crypto system. Now, before that, I should mention about something about the security in general. That certain requirements that given a message X, it should be computationally infeasible, okay, for anyone except alias to compute a signature y such that verification of x comma y is true, right? So there may be more than one y, that is fine. There may be more than one y. Collection of signatures are also possible. So if Oscar can compute a pair x comma y such that verification of x comma y turns out to be true, and x was not signed by alias, then signature y is called a forgery. Somebody has done that. Okay, this is a general security setup. Okay, so I think so these requirements, as I mentioned, looks like we can use RSA. So I'm going to give you the basic algorithm. Of course, there is a much more enhanced version available. So it is RSA signature scheme. Okay. So again, what you require, n is a product of two numbers, two large primes, p and q are large primes. And p and a is same thing as integer modulo n. Okay. Now I am going to define a this kind of k as n p q a b such that n is equal to p into q and a into b is congruent to 1 mod phi of n. Right, they're the basic requirements. So here the value n and b, these two pairs are public key, and p q a are private. Okay. Now, how do we define signing of a message? So for k is equal to NPQAB. We define signature with respect to K of X as, so once we have K, that means we have NPQAB, right? This as X raised to power A mod N. Okay. This is signature and verification. So once there is a pair X comma Y, this verification is true if and only if X is equal to Y raised to power B mod N, for X comma Y in integer modulo N, right? So here actually you can observe that Alice signs a message X using RSA description rule DK. So okay, so this signing is using DK here. If you recall from your previous RSA algorithm, so this is our signing, because this is a private, and verification algorithm use this EK encryption rule here, which is public, right? So because EK is public, this is private, right? So in under these settings, so you can see that so you can verify that if this happens, obviously it is signed because of all the settings of the RSA crypto system. This really works actually. Now there are certain observations here. If once we design this kind of RSA signature scheme, anyone can force this RSA signature scheme by choosing a random Y. Okay, choose this Y here as a random. Okay, and then compute EK. So basically, X is equal to EK of Y. Choose Y random, and then just compute this quantity. Then Y will be a valid signature. Okay, so on the X. Okay, so if this can be done, so basically this is kind of little bit weakness of this system. If you can actually choose random Y, and it turns out that encryption of Y is X, then the system is not secure actually. So how we can avoid forgery here? So let me actually describe some of the possible attacks in general also on the signature scheme. So there are two techniques which are used. One is, so message contains sufficient redundancy that a forged signature of the random business cannot be done. Second is we use hash function. So let us see, and then in that case security depends on the security of the hash function. So if you remember from a message X, we can always compute the hash function. So what are the attack models? Let me describe to you in general. key only attack. So if someone who wants to attack that Oscar is having public key, that is verification function. If this is possible, so this is known as key only attack, right? Second, known message attack. So if Oscar has pair of messages, a pair of signed messages, so that means if yi is equal to signature k of xi, then also, so this is a known message attack, okay? So what are the, adversary goals, that we can actually look at it? Uh, Goals as such, total break. How to break the system completely? If Oscar can obtain private key, right? Somehow get this private key, then you are done. Then selective forgery. In the selective forgery, with some non-negligible probability, Oscar is able to create a valid sign on a message chosen by someone else. So basically, what does that means? Given a message X, he can determine with some probability a sign Y, such that verification of the pair X comma Y is true. Okay, this is selective forgery. Then there is existential forgery. In this, actually, if Oscar is able to, create signature for more than one message, that means create a pair. So create a pair X comma Y, such that of course verification of X comma Y is true for more than one message. So there are these three kind of goals which Oscar wants to create. Okay. So now I think I'm going to describe the hash function business here, how a hash function will be useful. So let us describe that. So signature and hash function. So hash function, I hope you remember. So hash functions are functions from 0, 1 star to Z. Input messages of arbitrary length. Arbitrary length and output, we call it message digest of size, say 224 bits, right? If you remember why we need 224 bits. So message digest is actually signed rather than message using signature scheme PAKSV, where of course, so what you do, message is X, certain bits, right? Message digest you compute, which is say z is some function of hx. Z belongs to z bar, we can say the hash function, and signature is y is equal to z, and y belongs to y. So we transmit x comma y. So basically, we compute the hash function of the message. Okay, so message digest, and then we sign that message digest. Okay, and then you send x comma y. So now essentially security depends on the security of the hash function. So all the previous problems, which were there for the security of the hash function, we can do all that analysis here also. Okay. Okay, now I think I'm going to describe algorithm signature scheme. P is a prime such that discrete log problem in ZP is intractable, right? It's difficult. Choose alpha to be element of ZP star. So alpha is we are taking as a primitive element, right? So order of alpha is one less than the whole order of the group. Take P to be ZP star and A to be P star cross ZP minus 1. This K, we are taking key space P alpha A beta such that beta is congruent to alpha raised power A mod P. That is our key space. So what are the keys basically? P alpha and beta are public key and A is a private key. This A is a private key. Alpha is a primitive element, that is very, very important actually condition. So now if we take a key, this is capital K I am taking as P alpha A beta for a secret random number, small k I am saying, maybe something like this, k in ZP minus 1 star. Secret random k, we sign of this k, this is this k actually here, right? X and this small k here equal to gamma, this pair delta, gamma and delta. What is gamma and delta? So gamma is nothing but alpha raised for k mod p, and delta is equal to x minus a gamma times little k inverse mod p minus 1. Okay, so this is how you do the signature. So signature of, so for that key, right? So when we are taking this key here k and the secret number k, then we can sign this message like this: sign of k xk is equal to gamma delta, where gamma is alpha raised to power k mod p and delta is x minus a gamma times k inverse mod p minus 1. Why these numbers? It will be clear. I can show you why it works here. So actually, how do you verify? First of all, for x and gamma in ZP star and delta to be a member of ZP minus 1, verification algorithm works like x comma gamma comma delta is equal to true if and only if beta raised to power gamma times gamma raised to power delta is equal to alpha raised to power x mod p. At present, I mean, it looks like very complicated, but actually, let me show you how it works. Okay. So if I do, so basically, yes, if we consider beta raised to power gamma into gamma raised to power delta, this quantity, and just compute what happens, just substitute value of beta, you can see that value of beta is alpha raised to power a here, okay, and gamma is this quantity alpha raised to power k. So I can substitute these values here. This will be beta raised to power, sorry, alpha raised to power a gamma times alpha raised to power k delta, which is alpha raised to power x, since a gamma plus k delta is equal to x mod p minus 1. This is, if you look at the last line here, delta, this is, x is equal to k delta plus a gamma, right? So that works here. So in fact, I can show you the other way also. Alpha raised to power x is equal to beta raised to power gamma into gamma raised to power delta mod p. So this is equal to alpha raised to power a gamma plus k delta, right? Actually, this works because because alpha is a primitive element. Actually, this is very, very important actually. So alpha is primitive element if and only if actually x is congruent to a gamma plus k delta. So I think I can give you a small example here. P is equal to 467, P is equal to 467, alpha is equal to 2, A is equal to 127, beta turns out to be alpha raised to power A mod P is equal to 2 raised to power 127 mod 467 turns out to be 132. So suppose Alice wants to sign x equal to 100. She chooses a random number k, small k is equal to 213. Now one can check that GCD of 213 and 466 is 1. So basically, we can compute gamma is equal to 2 raised to power 213 mod 267 turns out to be 29. Delta turns out to be 100 minus 127 into 29. Okay. One can check that 132 raised to power 29 into 20 raised to power 9 raised to power 51 is congruent to 189. All these calculations I cannot do right away, but you can verify. And 2 raised to power 100 is equal to 189. Okay. Modulo 67. So signature is valid. Anyway, so I think that's all about signature scheme. So I guess I gave you very brief. So I'm just recapturing signature scheme consisting of two algorithms: signing algorithm and verification algorithm. Signing is done by a private key and verified by a public key. Okay. So this is the whole mathematical setup, and what kind of forgery, what kind of attacks are possible. Then we looked at RSA signature scheme, attack models, what are the total goals, signature and hash function idea. So basically take the message, compute the message digest and sign the message digest, okay, and send it, In fact, now there are a couple of more algorithms and a lot of other security analysis, which I am not doing it, that's all, okay. So I leave it for you. I mean, to verify a couple of, so for example, these things, you can just check on yourself, when you compute these things, So I think that's all for signature scheme. So next time we can start something new.